Okay, David, I think we're ready to record. Okay, so last time we went over the basic linear inverse, which is called a minimum norm linear inverse. So it's an underdetermined problem, which means you're solving for more things than you have data. You've got 300 sensors, and you're solving for 5,000 possible activations at 5,000 different locations in the brain. And so clearly that's not enough data. You need at least 5,000. If it's a linear problem, you need at least 5,000 data points to get 5,000 answers. So one of the ways of getting around this problem is called a minimum norm. It's kind of the opposite of a least squares solution, where you've got more data than you need, and you're trying to find the best fit. In this case, you have less data than you need, and so you need some additional constraints in order to actually come up with a single solution. And that constraint was the minimum norm, which means to find the solution, find an inverse that gives you a solution that has the smallest norm, which is just the Euclidean norm, meaning taking all the x, y, z, et cetera, et cetera, et cetera, and then just calculating the length of that vector. That's the Euclidean norm. So find this, come up with an inverse that gives you a solution that has the smallest norm. So that's the meaning of the linear inverse minimum norm solution. So what I'm going to talk about today is just finish up a tiny bit about that, on sort of calculating the point spread function, like how much blurring do you get from this inverse, and then what recommendations does it make for collecting data, like how many sensors to use of each kind, mixing MEG and EEG data. Then I'll talk about fMRI constrained. So one of the things that you might want to, that is an interesting possibility, is we could actually combine fMRI data with EEG data. What are the problems with sort of combining those two modalities to try to figure out where to extract the time course of activations in different parts of the brain. Then we'll talk a little bit about surface normal problems, because the whole reason to write FreeSurfer in 1990 originally was to introduce a surface normal constraint, and so what are some of the problems with that? And then last I'll talk about can we do any better than the minimum norm by using the spatial covariance, using the spatial patterns, sort of an analysis of the spatial patterns that appear in the data. So that's the grab bag of things. So let's start off quickly with sort of point spread, or crosstalk, and so what is the definition of that? So for point spread, the idea is if you've got some kind of source, a single source there, and so both of these things basically rely on the idea that if we take a point, so just a single point, meaning like a point, one source. So we take one source, and then we run it through the forward solution. So A was what we used last time for the forward solution. So we take a unit activity at one point in the brain, run it through the forward solution, figure out what it causes to all the sensors, and then just take that forward solution and just run it back through the inverse. So this is the inverse. So invert it, and then just see what we get. And so and then basically that will tell you how much blur. So if you just take one source, run it through the forward solution, and then you get back some big blob like that. So that kind of tells you, how much this data point, will sort of affect, other points around it. So it's like, the sensitivity of other points to you, to this point. But the opposite of that, the opposite of that is the crosstalk. I mean, you can see it's closely related to it, and the crosstalk is basically sensitivity of estimate at this location to activity somewhere else. So you get the same kind of data, and so the question is, how do other points cause crosstalk here? And this is the opposite of it, which is that how does this point interfere with other points? And both of them basically, so this sensitivity of other points to you, and this is how activity at other points affect you. So there's a good paper to read, a very clear written paper by Anders and Arthur Liu in the readings if you want to sort of go over this. Just look up Liu et al. I think it's 2003, 6, I can't remember exactly, but yeah, just look that one up. So, and it's basically based on this. Most of the math is based on take a point, get a forward solution, invert it, see how much blur you got. Do that a whole bunch of times for different points and see how they overlap. So from doing this kind of stuff, and then with different numbers of sensors, you can come up with some recommendations for which. So I won't go over all the math. You can sort of generally see how this is going to work, though, to sort of look at what kind of resolution is really practical to get, and how does the data sort of contaminate itself from different points. I mean, obviously, if you go way outside the crosstalk or the point spread, you're going to be safe. So you're easily going to be able to tell something that was here from something that was here. But when you're closer, obviously, there's going to be more ambiguity, and that's pretty much where the conclusions that I was relying on when I said, what do you practically have in terms of localization with EEG and MEG, and you practically have like 1 to 2 centimeter patches across the brain, but there's quite a few of those across the brain. So that's kind of the practical resolution. It's much less than functional MRI. Okay, so if we skip all the math and just say, what are the recommendations, because that's really, what are the practical recommendations? So it turns out that more is better, and that's true whether meaning sensors. That's true for EEG. So you can do better job localizing if you have more sensors. Not surprisingly, that's not rocket science. But if you have put on more electrodes, you're going to be able to do a better job of localizing. But another interesting thing is that EEG is better than MEG. And why is this? And this, again, is something that people knew for a long time. So if you've got, so the reason for this is if you've got a head, something like this, and there's a dipole somewhere in the head that's parallel to the surface of the head, then what that's going to do is that will cause the field to sort of wrap around that dipole. That's kind of the curl of the current. And so what that's going to do is that's going to make sort of a plus over here and a minus over here. This guy's plus and this is minus. But now let's consider what would happen if the dipole was perpendicular to the head. So if the dipole is perpendicular to the head, then, say, the current is say going like that, sort of coming out like that, that's going to cause the magnetic field to go around this way. And the result of that is that you essentially won't see any visible signal. So it turns out that a radial dipole, so if a dipole is perfectly radial like that, sort of perpendicular to the skull, when you work through the forward solution, you'll see that you don't get any signal at all. So, and that's not true of EEG. EEG will give you a signal, in either case. So, so this is, the forward solution, so 0B. But in the case of EEG, it'll work either way. So if EEG is like this, you'll get a big, positive. If that's positive current, you'll get a positive signal on the scalp. But if EEG is horizontal, what will happen is you'll get sort of a positive signal over here and then a negative signal over here, something like that. So in both cases, you'll get it. So EEG turns out to be better than MEG. It has better coverage because things that are exactly perpendicular to the signal just dies away. Now, as soon as the signal is a little bit off center, even if it was just as much as, say, like 20 degrees off, that's enough to start to give you a small signal, but a signal nevertheless in MEG. But because of this problem of, radial dipoles, this is just because radial dipoles invisible. So EEG is surprisingly better because a lot of people think, MEG must be better because it's more expensive. That's not true. But then another thing is that the biggest gain from adding small number of other type So if you have a lot of EEG and you add just a little bit of MEG, or vice versa, you have a lot of MEG and you add a little EEG, that gives you a much bigger gain than just increasing the number of MEG. So in other words, like if you had a choice between 100 MEG and no EEG and 100 MEG and say, 10 EEG versus 300 MEG, it would be better to have the mix. And that's not surprising because they're kind of giving you orthogonal information, the information that's at right angles to those two things. So it makes sense that. So it's always better. Now, given that it's easier, because more MEG easier, then like 300 MEG and 30 EEG is good. And you could do a little better by doing 60 EEG, but it's expensive to put on more EEG electrodes in general, and so even just having 30 EEG electrodes makes a huge difference if you're doing combined studies. Now, of course, combined studies are kind of a pain in the butt as usual because you've got the MEG helmet and then you've got some EEG electrodes on it, and so one possible thing that you can do is you can collect them at different times. So just collect MEG and then take the same subject and just collect EEG. It's not as good as doing them exactly at the same time, but it does make your life a little easier, assuming that the subject performs the same in both cases. And then finally, one thing that's worth commenting on, one of the big problems with combining them is you need to know what the ratio between them is. That's actually kind of a free parameter. So the problem is, like, for a given unit source, what is the the scaling factor between the EEG data and the MEG data. That's unknown. Now, you could figure it out by, you take an animal, implant a dipole, turn the dipole on, record the EEG, record the MEG, and then you actually figure out what that ratio is. But that's, so the, EEG, MEG scaling, that's not, you can't calculate that from the forward solution straightforwardly because you just don't know exactly what the conductivity of the scalp and the skull and all those things are. You don't have any direct measurement of that. And so the EEG, so what happens if you make a mistake? Well, like everything else, it causes blur. So if you make a mistake in this, it's going to give you a little extra blur. And there's occasional cases where you could measure it. If you have somebody, say, with an implanted array, you could run a little current through the array, through one of the electrodes in the array, and then actually measure what the MEG is and what the EEG is. But that's not generally applicable. If you have an implanted array, you generally have a hole in the skull, and so that's going to cause the forward solution to be kind of messed up. So anyway, that's our recommendations. So it's really good to combine EEG and MEG. And unfortunately, in the field, what's happened is that EEG and MEG compete with each other, because EEG people say, like, we're better than you because we're cheaper and we're sort of more, we don't need a giant expensive room. And MEG says, well, we're better than you EEG guys because we've got way more sensors. So there's a lot of sort of back and forth between EEG and MEG, but it turns out it's really good to combine them. And people don't do this as often as they maybe should, partly, like I said, because it's difficult to sort of do both at the same time. And people sort of tend to have expertise in one or the other. But if you can combine two experts and collect both types of data, that's a good thing. Okay, so that's the first topic. So now let's talk a little bit about fMRI constrained inverse. So when we calculate our inverse, we calculate strictly on the basis of the forward solution, invert the forward solution, and we get our inverse, and then we get some data, multiply it by the inverse, and we get our sources. So when we looked at that equation that we wrote out last time, where's that? Write it out in the same order. It's got to be here somewhere. Let's do it from memory. So our inverse matrix was equal to this covariance matrix of our sources, which we just assume, and then times the forward, that's the forward solution, and the covariance matrix of and that's the transpose of the forward solution, and then plus the covariance matrix of the sensor noise. So that was our inverse. So let's just quickly annotate this as source covar. So that means how correlated, what is our assumption about how correlated all the sources are? In the basic sense, we would say we don't know. They're just all uncorrelated. They're all independent. That's the most, and this was noise covar. And this was forward. So so each one of these are giant matrices all multiplied by each other and then with an inverse. So if we look at this, one of the things we have is this this source covariance matrix. And what is that? Well, that's just a giant matrix, sources by sources. So here's sources by sources. And down the diagonal, what we have is the variance. So this is the covar. How does every electrode correlate with every source correlate with every other source? And we could just assume that's 0. They're all uncorrelated. And then this is the variance down here. So the diagonal, which is like source 12, and over here, and source 12 over here, that's basically the variance. Now, normally we could assume they're all equally likely, and so give them all, say, 0.1. So they all have like a 0.1 variance. We're not assuming that there's any one that's more likely than another. But what we could do with the fMRI data is we could just collect some fMRI data. And so one thing we could do is we could insert the fMRI data in as our expectation of what the variance should be at all these different sources. So, for instance, we could say, well, here's some sources that correspond to, say, prefrontal, dorsolateral prefrontal cortex. So dorsolateral prefrontal cortex. And then here's some guys that correspond to, area MST. And so what we could do is we could just basically, insert fMRI data in there. So we could just insert some higher variances for expected variances. So these are prior. If you phrase it sort of in Bayesian terms, these are prior probabilities of activity being at this place in the brain, as opposed to what we started with was we don't know where the activity is. It's equally likely that it could be anywhere in the brain. So obviously this will affect your inverse solution a lot if you say, I think it's actually going to be here. That will help you a lot because that also implies I think it's not going to be here. And so, so what about all these other places? What do you do with them? So one thing you could do was say 0. So say I don't think it's going to be in any of those other places because we did an fMRI experiment, and then we made the assumption that whatever was appearing in the fMRI was the same as what was appearing in the EEG and MEG. And then we said, we're sure that there's going to be no activity at these places where there's no fMRI. So it turns out that's not a good thing. 0 is not a good thing to do. And so why is that? So let's imagine we have, there's some MST activity, maybe a little parietal activity. Say there was a little sort of inferior frontal activity. But let's just say, well, maybe there was a little bit of frontal eye field activity too. But that didn't show up. It didn't reach significance in our fMRI experiment. So this is the fMRI data. So fMRI data. So if we just slavishly take that fMRI data and just insert it into our inverse, but it turns out that this guy almost made significance, but not quite. Okay, so this, say the frontal eye fields almost came on, but they didn't quite. But now let's assume that they were detected in the EEG-MEG experiment. So what's going to happen is in the EEG-MEG data, there's going to be some signal coming out of these guys. And there'll be some, there'll be some signal coming out of these guys, and signal coming out of these guys, signal coming out of these guys. But now there's a problem. If we turned the expected variance down to 0 for all the different areas, then somehow these sources are going to have to explain this data. And so what will happen is somehow some combination of these sources, so basically these sources forced to explain, frontal eye field data, because we still have to actually explain the data that actually occurred. So that's not good. So essentially what that will do is it will force these sources to go through somersaults trying to explain this data. And so the way that you solve this problem is small. So turn these are the no fMRI points. So if we just put a very small number in there for our expected variance, what happens is effectively what will happen is the data from these guys, from this guy, will just get sort of smeared. It'll just disappear. So it will sort of be a more graceful solution. What it will do is it will sort of just absorb this data smoothly across lots of different parts of the brain and sort of disappear it effectively. So you might think, wow, that's not good. You just got rid of that. There's actually some data there. There is. Yes, there is. But it's better than trying to have these guys explain that data coming from a source that was actually there in the EEG and MEG, but which didn't reach significance in the fMRI. So many years ago in our original paper about this, we pointed out that you could insert data in this way, but you got to be a little careful so that you don't get sort of a pathological solution. Now, one misconception worth stamping out: a lot of people, when they think of fMRI and EEG or EEG and MEG, they figure there's got to be a way. We've got great spatial resolution. We've got great spatial resolution with F functional MRI, and we've got terrible spatial resolution with EEG and MEG. Can't we combine them and get the best of both worlds? Get time-resolved data at high spatial resolution. And the answer to that is no, can't do that. So why is that? Well, if you think about one of these, sources that is capable of actually being localized by the inverse, by our basic inverse, what is it? Well, it's about 1 to 2 centimeters. It depends on the depth, but something like 1 to 2 centimeters is it's a chunk. It's about something like that. So you can tell this apart from this, but within this range you don't do too well. Now that's a pretty big area. Now you might think, well, say the fMRI data actually showed there were 2 foci in there like that. The high resolution fMRI data said there's actually 2 independent inferior frontal sources. The problem is you still have to go through the inverse here, and so there's no way that the inverse can tell if the point spread function of your solution is wider than those 2 sources. How can this inverse tell which one it should go to? And so it's not possible to just It's not possible to sort of magically combine fMRI with EEG and then EEG and MEG, and then come up with a magical solution that is extremely high resolution and extremely high spatial resolution from the fMRI and extremely high temporal resolution from the EEG and MEG. The best you can do is you can in practice is that you end up being constrained to the spatial resolution of the MEG and EEG, but you have more information about exactly where on the cortex it is, where that big patch is, and you, by turning down the variance at places where you don't have the MEG and EEG, where you don't have the functional MRI, your MEG solution is cleaner, and there's less likelihood of point spread function blurring problems. So it's good to combine them, but it's worth sort of considering that that you just can't turn off the variance in places where you didn't have fMRI. That's not a good plan. Okay, so that was quickly across sort of combining fMRI data with EEG and MEG data to help your localization. So now let's just talk a little bit about the surface normal. So this literally was the original motivation for FreeSurfer. In 1990, we were trying to reconstruct the surface so that we could use all this good information about the fact that we know that local current tends to flow perpendicular to the cortex, and it doesn't tend to flow sort of tangential to the cortex. And so if we could reconstruct the cortex, then we could have a better inverse because then we could, instead of trying to guess what the orientation of the source was, we knew what the orientation of the source was. So it turns out it's a little more complicated in practice. So say we've got a sulcus like this. So here's a sulcus. There's the skull up there. And so it turns out that if we look at a dipole that's here versus a dipole that's only like 1 or 2 millimeters away, so like a dipole over here. So those two guys are really easy to tell apart, even though they're much closer than the 1 or 2 centimeters that I talked about. So if you're on a gyrus and you just go a couple millimeters, and now you're pointed in a different direction, the forward solutions of these two guys are extremely different. So this guy is extremely easy to tell apart from this guy. It's going to create a completely different spatial pattern on the scalp. So that's good. I mean, that's the part we were thinking of when we were first working on FreeSurfer. We said, it's all this great information about the exact angle of the dipole. That's going to create large differences in the forward solution and help us out. That's the good part. That's the good news. Good news. A, B, easily distinguishable forward solutions. So that's the good part. And having the cortical surface helps there a lot. But the problem is, if we look at another situation, which is, say we've got another gyrus over here, okay, another sulcus. Extend our skull out a little bit. So, unfortunately, it turns out that if you have a dipole that's, put them in a different color, if you have a dipole that's here, it's really hard to tell apart from a dipole that's here. And here, let me just straighten this out a little bit. And in fact, it can be hard to tell apart from a dipole that's even in the next gyrus over. So something like this. So it turns out it can be even hard to tell apart from this guy. So, and that's just because when you just move a dipole, so if you rotate a dipole, you get this huge change in the spatial structure of the forward solution. But if you just move a dipole, all you do is it just moves. It just like barely moves a little bit, and it's pretty difficult to pick up the difference between this and this in the forward solution compared to this, and this. So that's kind of an evil non-uniformity of the point spread function. That's what you would say. Like, these two things are very close together, easily distinguishable. These are quite far apart on the surface. This guy's really far apart on the surface. And so the bad news. Yeah, so the bad news is, so we'll put that in a different color. So the bad news is that, C, D, and E, hard to distinguish. Now there's a problem there, which is that this guy would be a negative dipole, right? So this guy is neg. Positive. So that's coming out. So that one's a positive dipole, but this guy's a negative dipole, and this guy's a positive dipole. So this guy's coming out. This guy's going in. Coming out. So the sign of the dipole will change, and so when you actually unfold the cortical surface, so if we unfold that, what do you get in your solution? Well, you get, here's our unfolded cortical surface. You'll get like a little patch of positive, and then there'll be a little patch of negative for the next sulcus, and then another little patch of positive, maybe even another little patch of negative. So that's kind of ugly. So what you could do, one thing you can do is you can just ignore sign. And I remember when we proposed this to EEG people, they are so wedded to the idea of N1 and P1 and sort of like negative and positive. They said what? That's all we have. We only have negative and positive. Now you're telling me to ignore the sign, and you're just going to say here's just the variance, basically. Square it. Here's the variance of the activity. It's been constrained by the the angle. So you're using the angular, you're using the surface normal. You're using this, surface normal constraint, and so you're doing a better job of localizing. But now you're telling me that I can't even tell what the sign is. So the EEG guys didn't like that. Although I think conceptually that one makes a lot of sense, but the EEG guys wouldn't have it. And so the other possibility is basically solve onto dipole triples, and this one is commonly used. And so how does this work? So this one basically says, well, we've got, so here's a sulcus again. And so what we do is at each point in our cortex, we just allow there to be a little dipole, an XYZ dipole triple. So we put 3 dipoles in at each point in the cortex instead of just a single one perpendicular to the cortex. So this essentially throws away some of the information that we have about the actual orientation of the cortex. But there's some advantages to it. So one advantage is that so if if our forward solution gives us, maybe some positive here, maybe some negative here, maybe some positive here, but notice right here in the bottom of the sulcus, there's no activity because the orientation of that guy is different. And so not only will you, let me just draw this a little bigger. So not only will you have sort of some negative, but there'll be a gap, and then you'll have some positive, and there'll be a gap, and then you'll have some negative. And so that's kind of spotty. It looks kind of, not only did you throw away the sign, but then it's spotty on top of it. That was just like completely beyond the pale. So the idea is that instead, solve on to triples at each cortical point. So this is still using the information about where you are in the cortex. But what it will do is it will get rid of the gaps. It will get rid of the gaps, and it will get rid of this alternation in sign. It doesn't use quite as much information as the orientation constraint, but because the point spread function of the orientation constraint is so weird, because you can tell A and B apart, but you can't tell C, D, and E apart. Just because of that sort of non-monotonic kind of weird blurring property of the surface normal constrained inverse solution. Usually people do this instead. So just put a dipole triple at each point in the cortex, solve onto that, and then you'll end up with one. You'll end up with one you'll get a little bit on this one, more on that one, more on this one, and so you end up with like a little single dipole, which may or may not be perpendicular to the cortex at that point. Okay, so that's the bad news about the surface normal problem and how to fix it. And then last but not least, this is something we did in our original paper from the 90s, and it's something that people still do. It goes under different names, but it's basically trying to use the spatial covariance of the sensor signal. So we talked about the spatial covariance of the sources. So this was spatial covariance of different sources, and then we talked about the spatial covariance of the noise in the sensors, but we didn't talk about the covariance of the data in the sensors. So that's another letter. We always have to use single letters, and so this is the spatial covariance in sensor data. Because when we record data, we get like a whole bunch of different spatial patterns that come out. And we might be able to actually kind of use that information about which spatial patterns appeared in our actual data to help us try to figure out where the sources were, but also where the sources weren't. So it's kind of a way, you can think of it as a way of improving your estimate of where the sources were not. So this was originally called, like in the 90s, it was called music. I can't even remember what that stands for, but it was called music. But there was a paper by Mosher and Leahy, if you want to go back and look at the original one. And then we modified it in our, Anders modified it in our inverse paper. There's a way to modify it, but there's another name for it. So sometimes people call nearly the same thing, beam forming. So you can see papers on beam forming, but basically what they are looking at the spatial covariance. So this is another important point here, is this is spatial covariance, calc across time window. So the idea is we have our data is changing dynamically. So the data is coming out of the sensor array, and there's all different spatial patterns appearing in it. And so you take a chunk of that data over time and calculate the spatial covariance from it. So what does that math look like? Well, before we do the math, why don't we just say, so how could this help? Yeah, we'll just sort of try to intuitively get a feel for how this could help. So say we have a situation. Say we have a situation like this, where we've got. We just draw a simple head like that. So say we've got two sources that are on at the same time like this. Now, at an instant in time, if those are on, those could easily be simulated by a source like that that's between them, slightly deeper, slightly deeper, slightly stronger. So because of just the ambiguity in the forward solution, the point spread function, we could easily end up with the minimum norm deciding that I want this, this dipole here, and this dipole, the total amplitude of that dipole is less than these two guys, and this guy will, this is kind of like a ghost source. This one will win the minimum norm competition. But if you think about, well, what if you had some data over time? What spatial patterns would you get? Well, sometimes they would be on at the same time, but at other times, maybe just this guy is on and maybe just this guy is on. And so what will happen is, at a single point in time, you will just get a spatial pattern that looks like that. But if you look at the data over time, at the covariance over time, you'll sometimes see that, you'll sometimes see something that's like that, and you'll sometimes see something like that. And so that gives you some extra information in a way that makes it easier to solve the inverse problem than just this. And so another thing is that that's one sort of practical example how this could help. But here's another practical example which is the one that we were particularly interested in, which was looking at the minimum norm sort of displacement of superficial sources. So say you had something like this. So you've got an actual deep source, but the minimum norm says I'm just going to replace that with some superficial guys that have a smaller norm. So the minimum norm will always give you this solution instead of a deep source. So now we can imagine two different situations in our spatial covariance. So the first situation is when we look across time, we always just get something that looks, so here's that, here's the forward solution of both of those, because they look exactly the same. So this is forward. So say if we look across time, we could look across several time steps, and we always find let's leave the dipoles out. we always find a spatial pattern that looks like that across time. In that case, we just have to sort of deal with it and just say the minimum norm is probably displaced to the surface. We can't tell which one it is. We'll just accept the surface. But an alternate possibility in your data, in your sensor data, is that sometimes you get a little surface dipole here, sometimes you get a little surface dipole here, sometimes you get a little surface dipole here. So if these are different, time points, and we look at the sensor covariance, we're able to actually distinguish these situations from each other by just looking at the data across time. So that's trying to give you sort of before we talk about the equations, give you a feeling for like how this could help, how sort of like looking at the spatial patterns in your data could help. And so in particular, the way the music was used very initially was, let's take the spatial, so what are the spatial patterns? So, and what do I mean by that? So if we take our spatial covariance, what is that? Well, it's just equal to all our data over time. Just multiply all the different possible combinations of vectors multiplied by each other. So if we write that out in more detail, we're gonna have to make some assumption about the noise. So we'll stick in some noise. That's our noise, and then basically we just do the 2-point correlations of every possible sensor. And what does that look like if we look at it from the forward solution point of view? That's a plus. Sorry. It just looks like we just sum across all possible combinations of sources. So here's our our variance of all our sources, and then we multiply that by the correlation, which is just basically taking a bunch of time points and multiplying the data at each pair of time points. At a given time point, take all the possible combinations of sensors and just multiply the data that you get at each pair. That's what all the correlation means. And then just sum it up across many examples. And then we have to run it through the forward solution. So here's the forward solution to get the sensor data. So here we're thinking of it from the point of view of starting at the source. We're trying to calculate these correlation of these sources, run it through the forward solution. This guy is ij. This guy's a transpose. Okay, so that's thinking of it from the point of view of the forward solution. But how do we sort of estimate that in real life? We just essentially take a bunch of data vectors and just multiply them all by each other. So that's what I was saying, incorrectly saying, as an explanation of this equation. So what is this? Well, you just have let's just do it for 2 points. So at this point, you've got some data over time. And at this point, you've got some data over time. And so, so what do you do to calculate this? Basically, you just say, let's just take the first time point and multiply that, and then the second time point, multiply it by that, the third time, multiply it by that, add the whole mess up, divide by the number of time points, and then you get one entry in the matrix. That will sort of like say, it's a diagonal matrix, so that'll say this entry here, that's the spatial, the sensor by sensor covariance matrix. So you get that will just go into this symmetric matrix as your estimate of the spatial covariance. Okay, so now you fill in all those numbers. There's 300 sensors, so it's 300 times 300 numbers. How each sensor is correlated with every other sensor. And then the question is, how do we sort of deal with that? Typically what we want to do is we want to kind of do principal components on it, something like principal components. So what we can do is we can sort of decompose it into a bunch of orthogonal components. And so what does that mean? It means let's decompose this covariance matrix into a bunch of uncorrelated, that's what orthogonal means, uncorrelated vectors. And what is a vector? A vector is a particular spatial pattern, because a vector is like just a number across each of the sensors. And what we want are orthogonal spatial patterns, which means spatial patterns that aren't correlated with each other at all. So this will basically, it will just divide this, these are all matrices, and we'll just basically divide this thing up into a bunch of eigenvectors. They're all perpendicular to each other. So if earlier in the thing we were talking about diffusion tensor imaging and eigenvectors. So here's the first eigenvector, the first column of this U matrix. So that's another eigenvector. So these guys are the columns. So these are the basis vectors, which are orthogonal, like XYZ axis of, sensor spatial pattern space. So what we're trying to do is just characterize all the different spatial patterns that occurred, but in this special way that we're dividing them into, we're just arbitrarily dividing them into uncorrelated spatial patterns. So that's what that U matrix is. These are basically the eigenvectors. Eigenvectors of, spatial patterns in data. The data that we recorded. And then it's multiplied by this eigenvalue. So this one says, how strong is each one? So these are here's the corresponding eigenvalue. So that's the eigenvalue for the first eigenvector. This just means, how strong is spatial pattern U1. So if there was a lot of a particular spatial pattern, like there was a tendency of this part of the data to go up and down over time, that would be a large variance for this particular spatial pattern. That guy would have a large eigenvalue, and they're sorted. So by the time you get down to down to here, this is the ones that don't explain much of the data. So those guys are kind of very small eigenvalues. So these guys are the eigenvectors, all perpendicular to each other, and these guys are the eigenvalues, which are how much is that particular spatial pattern. Each of these spatial patterns explain that. How much does that explain the data? And then it has to be squared. So there's U transpose here, because it's a variance and it's always squared. So that's why there's two of these guys. Okay. So now what we can do. So now what we've done is we've taken our covariance matrix, which we just calculated by just calculating all the correlations between each possible pair. we ran a singular value decomposition on it, or principal components on it. This is an SVD, which is, like principal components, not exactly the same, but similar. And we divided it up into spatial patterns, and then we cataloged them by how much of that spatial pattern occurred. So now that we have that, what we can do is we can say, well, these patterns didn't occur very much. The low eigenvalues didn't occur in our data set. And so what we can do then is let's go through our whole brain and go to each particular point in the brain. So there's a source here and a source here, possible source here, source here, source here, and there's source here. So we can just basically go through the brain, take each source, and ask, if we calculate the forward solution for that source, we get some. So calculate the forward solution for that source, and say that source gives us, a forward solution that looks something like this. So this is the forward for that guy. And then we can say, does that guy look like any of our data? Does it look like any of the spatial patterns in these eigenvectors that have the big eigenvalues? Or does it look like the spatial patterns in the eigenvectors that have the very small values? And if it looks like the small guys, then we can say, that guy, we're going to throw that guy out. So that's basically in words. I'll leave out the equations, but that's in words how this method works. So you start off with some sensor data. You calculate the covariance, which means just like take each pair of electrodes, multiply it for each time point, sum across time points, so that you have how much do these guys vary with each other? They could be positive, sometimes negative, sometimes doesn't matter. It's just a question of do they sort of have similar values across time, or opposite values? That's okay too. They could be negatively correlated. So that's our covariance, our spatial covariance of the sensors, the D. And then we take that and factor it into these principal components, basically. And what are the principal components? They're just a catalog of all the spatial patterns that occurred, weighted by how strongly they occurred. And that's what the eigenvalue means. How much weight does the U1 eigenvector have? And then you get all the way out. This is the UN. So this is the last eigenvector, which is really a pitiful eigenvector, which has a very small eigenvalue, and so that one didn't occur much at all. And then we go through our sources. So we go back to the sources, calculate the forward solution for each source, see what spatial pattern it makes, and then just see where does it fall in here. If it's in these noisy ones that sort of didn't occur, we throw it out. If it's in one of these ones that occurred a lot, we keep it. So that's fundamentally how something like a beamformer or the music method, or if you go back to the Dale and Serino 93 paper, where we sort of do a version of that. That's how it works. And this is potentially an independent piece of information from our basic minimum norm inverse, because it's a separate piece of information. It's the actual data, spatial structure of the data that occurred over time. And so that's one way of improving source localization. And it can sort of deal with the minimum norm problem. It can actually figure out, do you actually have a bunch of sources on the surface, or is there actually a deep source? If there actually was a deep source, you'd always get that spatial pattern. If there was a superficial source, sometimes you get little bumpy spatial patterns from the superficial one, and you would know actually, no, it's actually a superficial. It actually is a superficial source. Whereas if you get just patterns like this, that can't be a superficial source. And so the music would throw that guy out. We say like, no, it can't have been a superficial source because we never saw a spatial pattern in there that looked like one of these small bumps. Okay, that was a little rough, but hopefully you sort of got the idea of how we can get some extra information from this spatial covariance of the sensor data. Okay, sorry I went over. So I think we'll end there, David, and ask for some questions.